Let x and 1 be functions of p such that x of 0 equals y of 0 equals 1. If x of p is equal to the antiderivative of x of p plus the antiderivative of the antiderivative of x of p plus the antiderivative of the antiderivative of the antiderivative of x of p plus and so on, and y of t be similarly defined but this time with a factor of 2 on the right side, determine the value of x of 1 plus y of 1. This question is from the 2025 edition of the UP Mathematics Club's annual nationwide search for the Mac Wizard, which is a prestigious collegiate math contest in the Philippines. I have to admit that it's the first time I met infinite nested antiderivatives, and it got me stumped while watching the contest. A few contemplations later, and I figured that the solution here isn't quite complicated. For the solution that I will discuss, we will assume the convergence of the infinite sums. And to be honest, I'm not quite sure and haven't given it much thought whether or not there is enough information to claim convergence. The trick here is to take advantage of the relationship of the derivative and the antiderivative of a function. Recall that the antiderivative of the function x of t is the function whose derivative is x of t. And as a consequence of the fundamental theorem of calculus, the derivative of the antiderivative of a function is the function itself. It sounds confusing, but the point is that the derivative and antiderivative are effectively inverses of each other, so their composition simply cancels out. That is, the derivative of the antiderivative of x of p is simply x of t. It also follows from this that the derivative of the antiderivative of the antiderivative of x of t is simply the antiderivative of x of t. Extend this inductively to higher numbers of less said antiderivatives and say that the derivative of n counts of antiderivatives is n minus 1 counts of antiderivatives. So with that backdrop, let's generalize the given as f sub k of t being equal to k times the sum of the antiderivative of f sub k of p plus the antiderivative of the antiderivative of f sub k of p and so on. With this definition, x of t is f sub 1 of t and y of t is f sub 2 of t. Let's take the derivative of both sides with respect to t. We get that f prime of t is equal to k times f of t plus the antiderivative of f of t plus the antiderivative of the antiderivative of f of t and so on. Now here comes the interesting part. A bunch of terms on the right side is simply equal to f of t from our definition, granted of course that the infinite sum converges. We check here that the right side is this k plus 1 times f of t. We then have the differential equation f prime of t equals k plus 1 times f of t, which is a simple, variable, separable differential equation. So with standard records, we get that f sub k of t is a constant times e to the k plus 1 times t. For both x of t and y of t, we know that their value is 1 at t equals 0 as given. So the constant is 1 for both of them. Thus, x of t is e to the 2t and y of t is e to the 3t. P equals 1, the values of x of t and y of t are e squared and e cubed. Therefore, the required sum is e squared plus e cubed. And that's our final answer. If you have an alternative solution for this problem, or any comments, clarifications, or violent reactions, please let me know in the comments. Thank you for watching and see you on the next one. Bye-bye.